Hello and welcome to section 3.3, the increasing and decreasing functions and the first derivative test. So we're going to go over the examples, and remember, if you have any questions on these examples, please ask them when you come to class. So the first example here says find the open interval in which f of x is increasing or decreasing. So the first thing we have to do in order to find increasing, decreasing is basically check out the slope. We'll check when the slope is positive, it's increasing. When the slope is negative, it's decreasing. So we need to find those, what we call critical numbers, where the values are changing directions from increasing to decreasing and decreasing to increasing. And those critical values are the peaks and valleys in a graph. So if the graph looks like something like this, we would be looking for a horizontal tangent because that's where it goes from increasing to decreasing. Down here, we'd be looking for a horizontal tangent where it was decreasing to increasing. So in order to do that, we're going to find the derivative. So we're going to take the derivative of this function. It gives me 3x squared and minus 3x. And so there's the derivative of the function. If I do a little factoring, I get f prime of x is equal to 3x times x minus 1. Now, how do we find these guys? Well, that's where the horizontal tangent is 0, where the slope is 0. So that's the derivative. So we set the derivative equal to 0. And that would mean that x will equal 0 and x will equal 1 when we find out what horizontal tangents. So we're going to do a quick little test over here. I'm going to kind of draw like a number line, and I'm going to put 0 on here, and I'm going to put 1 on my number line. And basically these are my intervals. I'm going to put them actually up top. These are my intervals that I'm looking at. So 0 to negative infinity, and then from 0 to 1, and from 1 to infinity. So those are my intervals that I'm dealing with. And so now, in order to find out whether it's increasing or decreasing, we need to look at the slope of the line. And so if the slope has if it's a positive slope, then we could say the graph is increasing. If we had a negative slope, then we could say the graph is decreasing. And we know that at 0 and 1, it has a 0 slope because we just found it. So we're not going to pick those values. So I have to pick a value that is less than 0. So I'm going to do, and remember, we're putting this into the derivative function, so f prime of negative 1. So I'm putting negative 1 in here because that's between 0 and negative infinity. And I don't even care about the actual number. I just care about the sign, whether it's positive or negative. So I can put it into any one of these derivative functions, whichever one's easiest for you. And I'm actually going to put it in this factored form. I just think that's a little bit easier. So I go 3 times negative 1 times negative 1 minus 1. And you can see that I'm going to end up with a positive number when I do this. Negative 1 is negative 2. Negative 2 times, so we got two negatives being multiplied together. So at this point, we know we are increasing between negative infinity and 0. So then I've got to pick a number between 0 and 1. So I'm going to pick a half, so I'm going to do f prime of a half and plug it into the derivative function. And so if I plug it in there, I'm going to say, well, it's going to be f prime of a half is going to be 3 times a half times 1/2 minus 1. And in this case, you can see that I'm going to get a negative number over here, negative a half. And if I multiply all this out, this is going to be a negative number. So right now, my increasing intervals are from negative infinity is less than x, which is less than 0. My decreasing interval is between 0 and 1. And don't be fooled. Don't just think that automatically this is going to be an increasing function. Most likely it will be, but we have to check. And so we have to go through and actually check and see what's happening. And just in case, because sometimes they fool you and it's like increasing, increasing, or decreasing, decreasing. And so we got to check everything. So now I'm going to pick a number between 1 and infinity. And so f prime of, say, 2 plugged into this, you can see that I'm going to end up with all positive numbers. So my increasing interval is from 1 to infinity. So I have two increasing intervals, these two right here. And I have one decreasing interval, which is what they were looking for. So where are the intervals increasing and decreasing? That's what we're looking for. Now we can use this increasing and decreasing to help us find maximums and minimums. If you think about it, if I go from increasing to decreasing, I should have a maximum. If I go from decreasing to increasing, I should have a minimum. And that's what leads us into the next example. So this one, it says find the relative extrema of the graph in this interval. So as you know, that sine could go on forever, so we're not going to do that. We're just going to limit it to 0 and 2 pi. So if I'm looking for extrema, first thing I know is I need to find the critical numbers, which are the values where the derivative is set equal to 0. So I'm going to say f prime of x equals 1/2 minus cosine of x. So there is my function. And so our critical numbers are where there's maximums and minimums. And so basically what I do is I set the derivative equal to 0. So you notice this is the same process I was just doing. If I solve this, I get cosine of x equals 1/2. And then I have to remember on the unit circle, where cosine of x is equal to 1/2, and the cosine of x is equal to 1/2 when we are at pi over 3, when x is at pi over 3, and at, I believe, 5 pi over 3. So those are my intervals that I'm going to be dealing with. And so over here, I'm going to set up my, whoa, that was not a very straight line. All right, I'll try this again. I'm going to set up my little number line. And this time I only have to go from 0 to these numbers and to 2 pi. So I'm going to go from 0 to pi over 3. So 0 to pi over 3, from pi over 3 to 5 pi over 3 to 2 pi. So those are my intervals, and so I just need to figure out whether we're increasing, decreasing, or whatnot. So if I do f prime of, we need a number between pi over 3 and 0 that will fit into the derivative function. So I'm going to go with pi over 2, or pi over 4, excuse me. And so that we're in the interval. And if I put pi over 4 in, I end up with, well, let's see, I get 1/2 minus cosine of pi over 4, which is negative root 2 over 2, which means that I'm going to get a negative number. So this is a decreasing function right here. We are decreasing in the interval between 0 and pi over 3. So then from pi over 3 to 5 pi over 3, now I believe I can do pi over 2. And when I do pi over 2, cosine becomes 0, so I get 1/2, which is positive. So now we are increasing in here. And then last but not least, between 5 pi over 3 and 2 pi, actually, I probably would have been better off had I chose like pi instead of pi over 2, but that's okay. Let's do, well, if I would have chose pi, it still would have ended up being, let's see, if I put pi in, I get cosine negative 1. It's still positive, so it doesn't matter what I put, just anything between pi over 3 and 5 pi over 3. And, you know, so then I'm going to do prime of, let's try 7 pi over 4. Kind of the same idea as what I had before. And in this case, 7 pi over 4 for cosine is going to get me a, okay, it's going to get me root 2 over 2, which is negative from this, which means I get a negative number down here, which means we are in decreasing. So how does this decreasing, increasing, decreasing give me relative extrema? Well, I know that if the graph is going from 0 to pi over 3, we're decreasing. So here's pi over 3 down here. And then after pi over 3, I'm increasing. And then I increase until 5 pi over 3. And then I'm going to decrease after that. And so you can see that we have a relative minimum at pi over 3, and we have a relative maximum at 5 pi over 3. And that's really what we're looking for these guys. And basically, you know, they're relative because there's more of them. We just had to restrict the interval. So in our next example, they're asking us for the same thing. Can we find the relative extrema? So in order to do so, we're going to take the derivative of the function. So this time it looks like it's going to take a chain rule. And so when I take the derivative, I get 2/3 times x squared minus 4 to the negative 1/3. And then I take the derivative of the inside, which is 2x. And so then to simplify this, and I would highly recommend that you actually graph the original function to kind of see what we're looking at. because this is a function that we're not used to seeing, and it might give you a good idea of where the relative maximums and minimums are. Anytime you see a function that you're not kind of used to dealing with, yeah, you probably should graph it. So I'm going to get 4x over the cube root of x squared minus 4 times 3 to the 1/3 power. So that's what I'm looking at. And so now I'm just going to try to set this equal to 0, because that's what we do. So when we do these, though, our critical numbers are when the top is equal to 0, but we also have to take into account any places where the graph does not exist, because those could be maximum minimums. If they're like sharp points or something, they could be. So we're going to set 4x equal to 0, which means x is 0 is a solution. And then the possibility of the bottom equaling 0, we could say 0 equals 3 times x squared minus 4 to the 1/3 power. So I'm going to divide by 3, cube both sides, add 4. So x could be plus or minus 2 are my other two options. And so now we have to take into account that 0 is a critical number, and 2 and negative 2 are points of interest. And so when we set up our interval, we're going to go from negative infinity to negative 2, and then negative 2 to 0, and then 0 to 2, and then 2 to positive infinity. So it just basically means that we have a lot more places to test into this. So we're going to use this derivative, and again, it's all about determining positive and negative. We don't care about the actual number, so we're just going to look at signs. So I'm going to do f prime of, say, negative 3. That would be between negative 2 and negative infinity. The top becomes negative when I plug in negative 3. And on the bottom, when I square negative 3, I get 9. 9 minus 4 is 5. That's going to be positive. So that means that this is a negative, which means we're decreasing over here. Then between negative 2 and 0, a good number would be like negative 1. So I'm going to put negative 1 in here. Negative 1 means it's negative on top. And then on the bottom, if I put negative 1 in here, I get a positive. But then you'll notice that I'm going to end up with a negative 3 inside here. And no matter whether I multiply or cube root it, I still get a negative. So I have a negative over a negative, which means we have a positive in that area. So we are increasing. Then we are going to choose a number between 0 and 2, and which would be a good number would be 1. And when I put 1 in the top, I get a positive. And on the bottom, when I put in 1, you can see that I'm going to get a negative again. So this time we get a negative in that interval, so we're decreasing. And then last but not least, if I choose a number like 3, we'll plug in 3 on top, we get a positive. And then we put 3 in the bottom, we also get positive, so we are increasing again. So you can see the graph is going decreasing to increasing, increasing to decreasing, and decreasing to increasing. So basically what this will give me is that if it's going from decreasing to increasing, that negative 2, so we have a relative minimum at x equals negative 2, and we have a relative maximum looks like it's 0, because we're going increasing to decreasing. So we're going decreasing to increasing, something like that. So we have a minimum at 2. We're going from increasing to decreasing. So we have a maximum at x equals 0. And then if we go from decreasing to increasing, we have another minimum at x equals 2. So now if you wanted to find the ordered pairs, we would take the x values, plug them back into the original problem, and basically find out what they are. But we already know that these guys are our zeros, where our function was 0, so they're actually negative 2, 0, 2, 0, and 0, 0, or 0 and some other number will give us that one, will give us the value, because 0 doesn't actually. It gives us the negative 4th root, or yeah. So it's like 16, the cube root of 16. So that would be the y value. So you'd have to plug those back in to actually get those values. But those are the relative extremas. I mean, depending on whether they want them as points or whether they want them as ordered pairs or x's, so it just kind of depends. So then in the next example, same thing, we're finding the relative extrema, but if I'm going to go ahead and do this, and again I would graph this function so you can see what it looks like, because there are some things in here that's different than what you've seen before. First thing I'm going to do is I'm actually going to simplify this function, and since I'm going to divide both of these guys by x squared, I really get x squared plus x to the negative 2. It's just going to make my derivative a little bit easier. And so if I take the derivative of this function, I get 2x minus 2x to the negative 3. But then in order to find if I set this thing equal to 0 as it is, it's kind of a pain. So I'm going to rewrite this a couple times. Let's see, I got 2x minus 2 over x cubed. If I want to get x cubed on the bottom, I'm going to put x cubed over here and multiply the top by x cubed. So that would mean that I would get 2x to the 4th minus 2 all over x cubed. And so this is still my derivative, and now I think I've got it fairly simplified besides maybe factoring out a 2. So 2 on top would be x to the 4th minus 1 all over x cubed. And so now I set this guy equal to 0, and I solve. So if I set that equal to 0 to find my critical numbers, basically what I'm going to do is, okay, well, I have x cubed equals 0. So at 0, this thing doesn't work. There is nothing happening there, but that is a kind of that's not really a critical number. It's actually an asymptote because that's what makes the bottom 0. And so, but we still have to kind of check and see what's happening around that asymptote. And then for x to the 4th, minus 1 equals 0, we kind of need to factor this, which I would factor it as x squared plus 1 times x squared minus 1 equals 0. It's a difference of 2 squares to begin with. This x squared plus 1 is going to have imaginary roots, and we don't deal with those, but we have x minus 1 and x plus 1 when I factor it all the way down. So my other x values, that my critical numbers I'm going to deal with, are negative 1 when x is negative 1 and x is positive 1. So on my little table that I'm going to make when I'm doing my derivative test, I am going to set up so that I have an interval between negative infinity and negative 1, from negative 1 to 0, from 0 to 1, and from 1 to positive infinity. And I have to have all these intervals, and again, these will tell me what values are maximums, minimums, things like that. So if I go ahead and do the first derivative test, I'm going to do the first derivative test on, say, negative 2. I'm going to go back to, actually, I'm going to use this one right here because it seems either one of these guys right here just make my life a little bit easier. If I put negative 2 in, I get a, actually, no, I'm going to use this one down here. I like this one best. I'm going to use this guy right here. This is the one I'm going to use. And so if I put negative 2 in, I get a positive number here, and the top is going to end up being positive when I simplify it. And on the bottom, if I put negative 2 in, it's going to be negative. So at this point, between these guys, we are negative, and so we are decreasing between negative infinity and negative 1. So then I'm going to pick a number between negative 1 and 0, which would be something like negative a half. And when I plug in negative a half, well, let's see, negative a half is going to get me a positive number here, which is actually smaller, so the top is going to be negative. And on the bottom, a negative a half will remain negative. So now I have a positive number, which means I am increasing. And so at this point, if I go ahead and pick a number like a half between 0 and 1, I will end up with plugging in a half. That ends up that the top becomes, let's see, that's a negative number up on top, and on the bottom it's positive. So now I'm decreasing. But see, you might be thinking now that this line right here, that 0, is going to be a maximum because I'm going from increasing to decreasing. You know, it looks like it's going to do something like this. But remember, it's a vertical asymptote, and I just drew this dotted line here to represent it's a vertical asymptote, so it really doesn't have anything to do with it doesn't have anything to do with a maximum or minimum, even though it's going from increasing to decreasing, because the graph itself is like kind of like two U shapes on either side. And so, like I said, you probably should graph this if you haven't seen it before. And so then I'm going to do f prime of 2, and plugging in 2, I get a positive number on top, and on the bottom I get a positive number. So again, we are now increasing. So the only thing I have in this graph are two relative minimums, because I'm going from decreasing to increasing, decreasing to increasing. And so I have a two relative minimums at x equals -1 and x equals +1. And so those would be them, and you could go ahead and plug those values back into the original function to find out the y values that you'd get. If I put -1 back in here, I end up with 2 on top over 1, so the ordered pair would be -1, 2. If I put 1 in, again, I get 2. I get 1 comma 2. I get 2 for my y value. So those are the relative minimums if they're asking for points. There is no maximum, even though it kind of looks like it. When you have asymptotes, you got to be careful of those things to make sure that they are not in the equation. So this concludes our examples for section 3.3, increasing, decreasing functions on the first derivative test. If you have any questions, please come to class prepared to ask them. Thank you.